Welcome to lecture number 8 in relation with experiment number 2. And if you recall, last time I told you how to solve a first order linear differential equation and then applied that to solve the response of a series RL circuit which is connected to a DC source at t equal to 0, and this was the result of that, that is RL, and here was the switch, here was the constant battery voltage E, and the switch is closed at t equal to 0, and we have to find out the current in the circuit. I assumed the direction of the current in this fashion, and then I wrote down the Kvl equation as L di dt plus Ri is equal to your E, Kvl equations, and from which and then I just normalize this coefficient to 1, which is not necessary. You must understand, but I am habituated with that. That's why I am doing it. It is good thing to do like that. Anyway, this was the thing. And the response of the current with this condition being given to me, we got IT to be is equal to E by R into 1 minus e to the power minus R over L into T. Is not this is what we got. This thing, if you look, separate this out in two parts, you will find that it is equal to minus E by R into e to the power minus L by T and plus E by R. Is not? Therefore, this was obtained earlier, and this is the exponentially decaying term, and the final solution will be like that. Okay, so this is equal to IT. So this is the natural response, and this is the response due to forcing function E by R. Okay, and if somebody wants to know what is the voltage across the inductance, then also that is known. Vt, we know L di dt. You simply differentiate this fellow once and multiply with L. DC term differentiation will be 0. So that voltage across the inductance, if you differentiate, it will become E into e to the power minus R by L into T. And if you sketch these waveforms, you should sketch it like this. This is the time, this is t equal to 0, and this is the applied voltage. Applied voltage in this circuit was 0, not because shorted, but because there was no current existing, no voltage existent between these 2 points here. So it was 0, as if you have applied a stepped voltage of magnitude E. Then your current will be like this. Once again, with respect to time, you sketch the current waveform, which will be exponentially growing, and it will be like this. Final value is E by R. As t tends to infinity, this is 0. So this is I t. This is V supply, V in. Earlier it was 0, then and and then finally the voltage across the inductance will be, as you can see, it will be 0 in any case earlier, so it will be 0, then at t equal to 0 it shoots up to E, then exponentially decay like this. So this is the voltage across the inductance, how it varies with time. So many things can be studied, Therefore, across the inductor, voltage can have a step jump, no problem, and current. So this is the thing, and you have read it, but I told you. And I told you in a first order differential circuit equation how to write down the solution of the equation straight away. At this point, I would like to tell you one thing: concentrate on this term. That is the term solution due to forcing function. This term, this is the characteristic root minus r by L. M is minus r by L. So it was there. And this term, if you look at, when this right hand side is constant, then solution due to forcing function, you need not go to all those steps, k1 into x, this, that. You simply suppress this term, ddt term, and get the value of I from this equation. Suppress this. So value of I with this term suppressed will be equal to E by L by R by L, and that will be equal to E by R. So in one stroke you can write it. Anyway, do in whichever way you want to do, but this is just one observation I am telling. If the right hand side is a constant, solution due to forcing function will be also constant, and at that time there will be no time variation, so suppress this term and get the value of this term one can get. Okay, let us now proceed with some RC circuit. Okay, so similar problems you have done earlier. Suppose you have an RC circuit like this, and you have a switch and a battery voltage, and suppose the battery voltage is E, ideal battery, okay, and this is some resistance R, this is some capacitance C, and I will close the switch, and would like to know how the current varies. This will be one observation, and also another unknown will be the voltage across the plate of the capacitor. These are the two unknowns. Okay, so the thing is, this Vt and It are related because of this capacitor. So this is It, and we know It is equal to C dV dt. This is the thing. And it is given that voltage across the capacitor plate at T0 minus is 0, like this. So It and voltage across the plate of the capacitor are like this, and this is the thing. Therefore, and voltage drop across the resistance is Ri. Then I will apply the Kvl rule. So I start from this point, from this to this plus E, from this to this minus Ri, and from this to this minus Vt, voltage across the plate of the capacitor at any time t, and that must be 0. Or what you can say is this: Ri plus V. Let me go first because this you must be doing. So just do like this. Now there is one energy storing element, so it is expected I will get a first order linear differential equation. We will see if there are two energy storing elements, then the order of the differential equation will become 2 and so on in general. Therefore, now I will use this equation and put it here so that it will become RC dV dt. For I write C dV dt. Isn't it? Plus V is equal to your forcing function E. And then next step, what I usually do is dV dt plus 1 by RC into V is equal to E by RC. So it is a first order differential equation. Always try to get a differential equation. Don't try to get a equation where integration term is also there. For example, here for Ri, suppose I want to write down the Kvl equation in terms of I only, then the voltage across the plate of the capacitor, I should have written it as ITT by C. No? Then it will be a equation involving I only in this place of V if you substitute this. But this is not a differential equation. It involves in integration. So it is better in a circuit where in whichever branch capacitor is present, assume the voltage across the plate of the capacitor and then tell the current through that branch is C dV dt. Then it will lead to a differential equation only. RC is are of course constant, this one. Now here you can see the solution of this equation. Now this time I will write down straight away, no further this thing. Only thing I will write, characteristic equation is AM plus 1 over RC is equal to 0. That is the characteristic equation with the right hand side 0. So root is minus 1 over RC. This I will do. And then I will straight away write the voltage across the plate of the capacitor will be some constant into e to the power minus 1 by RC. That is, it will be, suppose that constant is A into e to the power minus t by RC. You know? And then the solution due to forcing function. And solution due to forcing function will be, if you suppress this term, dV dt term, it will be E by RC over 1 by RC. Means E. So the solution is in straight away, it will be like this. I skipped many steps to obtain this result. The way I told you, the solution due to forcing function is a linear combination of the forcing function and its higher order derivative. Same thing you can do, you will end up with the same equation. That is the thing. Now then I will apply boundary condition that V0 is equal to 0. Because this is no delta function, so V0 minus equal to V0 plus equal to 0. So V0 is equal to 0 will give you A to be equal to minus E. Therefore, voltage across the plate of the capacitor will then become E into 1 minus e to the power minus t over RC. So voltage across the plate of the capacitor will exponentially rise from 0, like this. It was 0, then it will go exponentially, and asymptotically it will reach this final value E. This is the voltage across the plate of the capacitor against time. About time constant, 1 by RC is called the time constant of the circuit, as L by R is the time constant of the RL circuit. So by the time it will reach 67 approximately percentage of the final value, that is called time constant. Anyway, this is the thing. Voltage across the plate of the capacitor was 0 before t is 0, then exponentially it will rise like this. Okay. Now if you are interested to know the current, then you need not solve another differential equation, because Vt has already been obtained. So It is equal to C dV dt, and if you do this, it will become E by R into e to the power minus T over RC. That's all. That is It. And so if you sketch the current, you will see that if you sketch this below this, so current will look like with synchronized with this curve, t equal to 0 is this point. So current was 0 and suddenly it goes up and then exponentially decay. The value it will go up is E by R. Is not, and I can verify that, because at t equal to 0 plus, voltage across the capacitor plate is 0. Therefore, all the voltage E is appearing across R. Therefore, at t equal to 0 plus or at t equal to 0, it has to be t 0 plus, it has to be this, and then it exponentially decays to 0. So, this is how I have to get along with the solving a circuit having energy storing elements. You have to write down some Kvl equation, and then you, depending upon the situation, if it is a first order system, you can solve those circuits, and classically you solve them, and no time should be wasted in writing down the final solution, at least nature of the solution. When the supply is constant, right hand side is constant. Okay, that is how we will do it. Acha, now I will tell you about, I will give you several interesting examples as your part of the lab problems. You have to solve them and send me. Based on that, I will evaluate you. Whatever I have taught so now, that I will give in a day or two. Okay, and I will also specify by what time you have to submit those problems. Acha. Now, finally, I will tell you about what to do with this one. And RLC circuit, RLC series circuit. Transient response I want to study. Here is a switch, here is R, here is L, and here is C. So R, L and C unknown, and here is a battery which I am going to connect across this series combination at t equal to 0. And here it is expected there will be transients because initial, there are two energy storing elements, and we also expect that the resulting differential equations will be what? A second order differential equation. Let us first write that. What we will assume is this: voltage across the plate of the capacitor at any time t to be Vt. Then I am sure the current It is no extra unknown. It is equal to C dVdt. Okay? So I will try to form a differential equation involving one variable, in this case voltage across the plate of the capacitor. So this is the current. Mind you, what is the voltage drop here? This is It plus minus Ri. Is not? But I is C dVdt. Similarly, what is the voltage drop here? Current assumed in this direction, It. Therefore, L di dt is the voltage. L di dt is the voltage. Therefore, I will write down the Kvl equation starting from this point, say, from this to this it is plus E, then from this to this minus Ri, from this to this minus L di dt, is not? And from this to this V, so minus V, and that must be 0. Or I will say L di dt, I am sorry, here is a I there, L di dt plus of Ri plus of V is equal to E. This is the differential equation. And this differential equation, since it is now known, what I will do is, there are, you see, two unknown present here, I and V. Translate it into one unknown. That I can do with the help of this equation. So wherever It is there, I will convert it to dVdt form, so that it will become Lc d2V dt2 plus Rc dVdt and plus V is equal to your E. This will be the differential equation. And as I told you, I will do it in this fashion, and I will normalize this coefficient of the highest order to 1. So divide by Lc both the sides, so that it will become equal to d2V dt2 plus R by L, Cc cancels, and dVdt plus V, and that is equal to E over Lc, because I have divided both sides by Lc. So this is the differential equation. It is a constant coefficient linear second order differential equation with only one unknown or output as voltage. Suppose I am interested to know how voltage changes with time when an RLC circuit is switched on to a constant voltage E, and this is the equation. Okay, and here I missed another term, 1 by Lc, because I have divided by Lc, na? So 1 by Lc into V. So this is the final equation, and in the next class we are going to solve this equation, how to solve a second order differential equation. I'll just tell you the steps. Thank you.